At this point, we now begin with chapter 3 of the course, which is to do with continuous functions. Okay, so again, this is continuity with respect to real valued functions. Alright, so before I define formally what continuity is, let me just mention formally that we are restricting ourselves to real valued functions. So in particular, let f with a domain A to R be a function under consideration. With the domain A being some subset of R. Okay, so that's going to be the implicit restriction that we are going to be making throughout our discussion. Okay, so we already have some sort of an intuitive understanding of what it means for a function to be continuous at some point, right? So if I'm looking at some point x0, let's say, which is in the domain of the function, what we mean by saying that the function is continuous is, of course, that, well, if you're trying to plot the graph of the function, then you will essentially, the graph is basically passing smoothly at the point x0. In other words, I can draw the function f in the neighborhood of x0 without, well, lifting my pen, so to speak, right? So I can kind of do this, and when I passed this point, I didn't really have to raise my pen in order to plot the picture. That's, of course, a very high schoolish definition of continuity, but that at least gives you the correct intuitive feel for continuity. Now what we will do is give the definition, the formal definition of continuity in terms of the language of limits that we have already become accustomed to. Okay, so formally f is continuous if the following condition is true. So f is continuous at some point, let's say x0 in its domain, if for all epsilon greater than 0 there exists a delta greater than 0 such that x belonging to the domain and x being within a delta distance of x0 implies that the function value at x is within an epsilon distance of the function value at x0. Okay, so that's your definition, formal definition of continuity. If you think about it, what we are capturing intuitively is that as x becomes close to x0, f of x should become close to f of x0, right? And how do I formalize that? If I set any error threshold on the function values, let's say epsilon, so then there is a small enough neighborhood around x0 such that for every x which is in the domain and within a delta neighborhood of x0, the function value will also be within an epsilon distance of the function value at x0, right? And again, the epsilon is arbitrary, so it captures the fact that as x becomes closer and closer to x0, f of x becomes closer and closer to f of x0, right? That, I hope, is the takeaway from this definition. Okay, so this is the first definition that we have for continuity of a function at the point x0. Now, one thing I should clarify is that implicit in this definition and in our entire subsequent discussion is that this x0 should somehow not be an isolated point in the domain, right? Because then then it's not even meaningful to ask whether the function is continuous at that point, right? So implicitly we assume that, let's say, for some, let's call it epsilon tilde greater than 0, either you have that the interval from x0 minus epsilon tilde to x0 plus epsilon tilde is a member of the domain, or, well, at least on one side So something like x naught to x naught plus epsilon tilde. This is a part of the domain, or x naught minus epsilon tilde to x naught. Right? So I don't want x naught to be some isolated point in the domain. Either there should be some interval on either side of x naught that belongs to the domain, or on any one side. But one of these three I implicitly assume, right? Otherwise the definition is not particularly meaningful. Okay, so with this I reiterate, a function is continuous at x naught if, as the argument of the function becomes arbitrarily close to x naught, the function value is also arbitrarily close to the function value at x naught. Right? That is what I mean by saying that the function is continuous at x naught. So it turns out that there is actually an equivalent way of talking about continuity, and that is in terms of sequences and sequential limits. Okay, so I'm going to write that equivalence in the form of this theorem. F is continuous at x naught if and only if the following is true. For every sequence xn in the domain such that xn converges to x naught, we have that f of xn converges to f of x naught. Right? So this is a well, the equivalence implies that this is in fact an equivalent manner of even defining continuity of a function at a point in the first place. And by this definition, a function is continuous at x naught if and only if for every sequence you can find in the domain which converges to x naught, the sequence of function values, right, f of xn, also converges to the function value at x naught. Intuitively, at least, it should be clear that this also implies the same intuition as the original definition, namely that as the function values become closer and closer to x naught, as the argument values become closer and closer to x naught, so do the function values become closer and closer to f of x naught, right? So this definition tells you that this notion in terms of sequential limits, so for every sequence xn converging to x, f of xn converges to f of x naught. This is equivalent to our original definition before. Okay, so let's see how this goes. So first, let's prove one part of this, which is the forward implication. That is, I assume that the function is continuous at x naught, and I want to show that for every sequence xn converging to x naught, you have f of xn converging to f of x naught. So assume f is continuous at x naught. Okay, now I need to pick any sequence xn in A such that xn tends to x naught, right? And what we have to do is prove that in this case f of xn will also converge to f of x naught. So to prove right, so this is what we need to show. Now this is fairly straightforward to show. Just go by the definition of the limit and of course apply the definition of continuity that we have available. Right, so you pick any epsilon greater than 0. Now, what can I say? What I can say is that by the definition of continuity, I know that there exists a delta greater than 0 such that if x is within a delta distance of x naught, then in fact the gap between the function values at x and x naught should be less than epsilon. Right, so there exists a delta greater than 0 such that, well, any x in the domain which is within a delta distance of x naught will satisfy the condition that f of x minus f of x naught is less than epsilon. This follows from the definition of continuity in the first place. Now, we also additionally know that the sequence xn converges to x naught, right? Which means that by the definition of that convergence, there exists, let's say, some n naught in n such that xn minus x naught is less than delta for all n greater than equal to n naught, right? Because xn is greater than x naught, for whatever delta I got from the previous definition, there is also a certain n naught beyond which the entries of the sequence are indeed within a delta distance of x naught. So all you have to do is patch these two together and conclude that in fact f of xn must therefore also be within an epsilon distance of f of x naught for all n greater than equal to n naught. Right, and that completes the argument. Right, because we know that for all n greater than n naught, xn is going to be within a delta distance of x naught, and that further from this implication tells you that f of xn must also be within an epsilon distance of f of x naught. Right, and that's essentially all there is to prove this side of the implication. Okay, so we have shown that if the function is continuous, then it satisfies the property that for any sequence xn converging to x naught, f of xn converges to f of x naught. So now it remains to prove the converse. Right, so I prove this side of the implication. Now, this side of the implication means that for every sequence, this is the hypothesis. For any sequence xn taking values in the domain such that xn converges to x naught, you have that f of xn converges to f of x naught. Okay, so this is the hypothesis. We have to prove that in fact f is continuous, right? So for the sake of getting a contradiction, let me assume the contrary. To obtain a contradiction, suppose f is not continuous at x naught. Okay, so now let us see what does this negation mean? What does it mean to say that f is not continuous at x naught, right? So this is the part where you just have to go back to the definition of continuity and figure out for yourself what is the negation of that definition going to be. The negation in fact implies the following, that there exists an epsilon greater than 0, right, such that for no positive delta does the condition hold that if x is within an epsilon within a delta distance of x naught, f of xn is going to be f of x is going to be within an epsilon distance of f of x naught, right? So there exists some positive delta there exists some positive epsilon for which the definition does not apply. What does that mean? Such that for all delta greater than 0, there exists an x in the domain such that x minus x naught is less than delta, and f of x minus f of x naught is greater than or equal to epsilon. Okay, so this is the correct negation of that statement. The original statement was that for every epsilon there is a delta such that being within a delta distance of x naught implies that the function value is going to be within an epsilon distance of f of x naught. What is the negation of that? There exists an epsilon such that I cannot find a suitable delta. In other words, there exists an epsilon such that for every delta, I can find a point which is within a delta distance of x naught, but which does not satisfy the function value nearness property. That is, f of x will in fact be greater than or equal to an epsilon distance from f of x naught. Okay, so this is what we mean by saying that f is in fact not continuous at x naught, and we will show that in a moment that this implies that the earlier hypothesis, namely that for every sequence xn converging to x naught, f of xn converges to f of x naught, is in fact not true. Okay, so now what I can do is for delta equals 1 by n, I can pick, let's say, some point xn such that, well, on one hand, xn minus x naught is less than 1 by n, because I'm choosing delta to be 1 by n. Okay, and f of xn minus f of x naught is going to be greater than or equal to epsilon in absolute value. Okay, so effectively what we have done is constructed a sequence such that xn minus x naught is less than 1 by n. However, f of xn minus f of x naught remains, well, greater than or equal to epsilon in absolute value, right? So for this sequence, clearly you can see that xn converges to x naught, but f of xn is in fact always more than an epsilon distance away from f of x naught. So you couldn't possibly have that f of xn converges to f of x naught, and that gives you a contradiction to the hypothesis. Right, and that completes the argument. Okay, so once again, the moral of the story here is that the function being continuous is equivalent to saying that the function being continuous at x naught is equivalent to saying that for every sequence xn converging to x naught, f of xn will in fact converge to f of x naught. Okay, so that's the first thing that we had to say about continuity. So before we do examples, I want to give you a couple of quick definitions. So if f is continuous at all elements, if f is continuous at all x which is in some subset of the domain, we say f is continuous on S. Right? Similarly, if f is continuous at every point in the domain, we just say f is continuous. Okay, so with this, let's actually look at a few definitions of continuity. Sorry, a few examples of continuity. Alright, so let's begin with a function of this sort. Let's say f of x is equal to 2x square plus 1. And my claim is that this function is continuous on R, which is the domain of the function. Okay. So this is fairly easy to show. How would I go about showing this? Well, if you think about it, given the background that you already have, it is not at all difficult for you to apply the original definition of the epsilon delta, the epsilon delta definition of continuity to argue that this is in fact true, right? But you will in fact notice that using the equivalent sequential definition of continuity is in fact far more elementary in this case, right? So pick any x naught in R, right, for any sequence xn such that xn converges to x naught, we know from our earlier machinery that in fact the sequence 2xn square plus 1 in fact will also converge to 2x naught plus 1, right? In other words, f of xn in fact converges to f of x naught, right, which implies that f is continuous at x naught. And since x naught is any element of the domain, it follows that f is in fact continuous. The only point I'm trying to make in this example is that to apply the original epsilon delta definition is very doable. I leave that as an exercise to you. But it's much easier to just invoke the sequential definition and show that, you know, through that definition the function is continuous. All right. Now let's look at another example. In this case, f of x is defined as follows. F of x is equal to, let's say, x square sine 1 by x for x not equal to 0, and f of 0 is equal to 0. Now, formally at this point of the course, we haven't really introduced or even defined sinusoidal functions. But if I was to only restrict myself to polynomial type functions, we wouldn't be able to do very many examples. So I'm going to just pretend that for the purpose of these examples, you know the definition of all of your trigonometric functions, which of course you do. Later in the course, we will formally define these things, right? So at this point, let me just pretend that you guys know your way around sinusoids and so on. All right, so this is the definition of the function. For x not equal to 0, the function is defined as x square sine 1 by x. F of 0 is in fact equal to 0, right? The claim here is that the function is in fact continuous at 0. Okay, and I leave it for you to actually show that this is in fact the case. How would you show this? All you have to do is argue that for any sequence that converges to 0, f of that sequence, so f of xn, will in fact also converge to 0. Once you can show that, that in turn implies that the function is continuous at 0. Okay, let's move on to another example. This example is f of x is equal to 1 by x sine 1 by x square. Okay, again for x not equal to 0, and f of 0 is defined to be 0. Okay, so here is another function. The claim in this case is that f is in fact not continuous. So when you are not continuous is called discontinuous. Discontinuous at 0. This is the claim, right? How would I go about arguing this? By the second definition of continuity, we know that all I have to do is demonstrate an example of a sequence that converges to 0 such that f of xn, the function evaluated along that sequence, in fact does not converge to 0, right? So in this particular case, well, I mean, again, you guys are better at this than I am, so go back and sketch what this function looks like to get some feel for what its behavior is around the origin. What I'm going to do is construct a sequence such that I'm riding along the peaks of the sinusoidal function, right? And then show that along that sequence, the function value will in fact tend to infinity. So let's see how that works. So I pick xn such that, let's say, 1 by xn square is in fact 2 pi n plus pi by 2, right? Again, we haven't defined pi yet formally the way we have defined e, so all of this is coming ahead. This is just for illustrating this example. I'm going to pretend that you are indeed comfortable with these things, which you are. We just haven't, we are not just going completely sequentially in the course, that's all, right? So I pick xn in this manner. The consequence of this, of course, being that sine of 1 by xn square is equal to 1, right? So in this case, it's clear that xn tends to 0, but f of xn, see, because the sine term is always 1 and 1 by x is in this case going off to infinity, so this fellow will tend to infinity, right? So this in fact shows that this function is discontinuous at the origin. All right, so there is a couple of more trivial consequences of this definition that we'll explore in this video. So suppose that for simplicity, let's say that f and g are continuous at some point x0, okay, and just pretend that f and g have domain R. You don't really need this for the result I'm about to state, but it just makes life easier to not have to worry about all sorts of funny corner cases. Okay, then the following statements are true. 1. If you take the absolute value of f, this is continuous at x0. The second is that if you multiply f by a scalar, this is also continuous at x0. So if you take a function which is continuous at x0, well, its absolute value, the function which is defined by its absolute value, is also continuous at x0. Multiplying by a scalar is also continuous, you know, at x0. If you add two functions which are continuous at x0, well, that sum function is also continuous at x0. Well, multiply functions that are continuous at x0, well, the product is continuous. If you divide them, the ratio is continuous so long as g of x0 is not 0. Right, and then finally the max of f and g is continuous. Okay, so again, the proof is remarkably straightforward, right? You just apply the sequential definition of continuity, and then it will just follow straightforwardly that all of these properties in fact hold. The last one may require one element of thought. So again, I'm going to leave this as an exercise to you. This is in fact, yeah, just an application of your, of your understanding of limits to argue that all of these things hold. For only the max, let me point out that what you can use is the following property. The max of any two numbers x and y, in fact, can be written as x plus y by 2 plus half of mod x minus y. Okay, again, stare at this for a bit and see that indeed whether x is more than y or x is less than y, you always have that max of x comma y is in fact equal to, well, x plus y by 2 plus half mod x minus y. Okay, you can use this preliminary, if you will, to basically show that property 6 of the theorem holds given all the previous properties that you have already in fact shown. Okay, so overall this result is an exercise for you to prove. The trivial consequence of all of this is that, well, any rational function and any polynomial function is necessarily continuous. So rational functions are basically ratios of polynomials. Right? Of course, when I say rational functions, because they are ratios of polynomials, implicitly I mean that rational functions are continuous at all points where that denominator is not 0, clearly, right? At all such points, in fact, rational functions are also continuous, right? So this is a trivial consequence of, in fact, the theorem that I have just written above. Okay, there is one final statement we will do before wrapping up this video. This is, in fact, this is trivial, but worth mentioning nonetheless. If f is continuous at x0, and let's say some function g is continuous at f of x0, then the composition function is continuous at x0. Right? And again, in this, implicitly you can assume that f and g have domain R. Right? So why am I saying this for both the previous theorem and this? It just makes life easier. So let me go back to the previous theorem, right? Why do I assume implicitly that f and g have domain R? Because when I add two functions, it is possible that, at points that are close to x0, f is well defined but g is not well defined. In which case now you have to ask yourself, where is the sum function well defined? Well, the sum function is well defined only at the intersection of those points where f and g are both well defined, and so on. So just to not have to worry about those kind of messes, I have assumed that both f and g are well defined over R, and more specifically f and g are well defined in the neighborhood that I care about, which in the case of this previous theorem is in fact that they are well defined in some neighborhood of x0. In this particular case, well, I need that f is continuous at x0, which means that f should be well defined in the neighborhood of x0 and g should be well defined in the neighborhood of f of x0, right? So it's primarily that we need for this statement. And in fact, the composition function is in fact also continuous. Okay, so this is also a trivial exercise, but in fact it has a one-line proof, so we can write it right away. It's just once again exploiting the sequential definition of continuity, namely that if I pick an xn which converges to x0, this would imply that f of xn converges to f of x0. Right? This comes from the fact that f is continuous at x0, and the fact that g is continuous at f of x0 implies that g of f of xn in fact converges to g of f at x0. Right? And that essentially completes the argument. Right? So I hope this is clear. When this composition function at x is simply by definition g of f of x. Okay, that's what I mean by the composition function. Okay, so what we have shown is that when you add continuous functions, you get continuous functions. When you subtract them, you multiply them, you divide them, you take the max of two continuous functions, and when you compose them, in all these cases, in fact, the resulting function is also continuous. Okay, so we'll stop here. In the next video, we will explore other implications of continuity with respect to boundedness and so on.